Hi everybody. Everybody should have a handout I just passed, right? They're it's not an assignment, it's like a reference sheet for a second. Shaw's one needs one. Pass it back. There you go. So what we're gonna be talking about today, and for chapter 5, are these trig identities. So, when I was a student, like a high school student, this particular topic I felt like was the one that taught me the most about algebra somehow. You'll see why here in a little bit. But this was my favorite topic as a math student in high school. So the idea here is we're going to be doing trigonometric proofs. Don't panic. They're not like the geometry ones. These will be algebraic. So you're just basically going to be stringing equivalent statements together. And really what we're going to have are 2 sets of tools. The first set is our identities. So you can use the sheet that I've just passed to you. We'll talk about how to use these in a moment and what they're doing. And the other set of tools are going to be algebra. So things that you might want to do. You may want to factor an expression. You may want to FOIL an expression. You might want to combine like terms. You might want to add or subtract fractions, i.e. making a common denominator. Those are the obvious things that come to mind right away. We'll add to that list maybe as we go if we come up to other things. Everybody's okay? So before we dive in and start looking at doing these things with trigs, let's take a step back and kind of review some of these basic algebra skills using just like some polynomial expressions that we would have done last year in our Algebra 2 course. So here it says expand the expressions using FOIL. Remember, FOIL stands for first, outer, inner, last. So if I have y plus 2 times y plus 7, what are we going to get when we multiply the firsts together?
Y squared.
Y squared. And then, when we do outers, 7y, 2y, plus 14.
Y squared, 9y plus 14.
So y squared plus 9y plus 14. Everybody feels comfortable foiling? If I look at the second one there, is that any harder for any reason? Maybe the multiplication is a little harder because you have numbers and variables now to multiply, right, at the same time. What do I get when I multiply the firsts together? 6b squared. Say it loud and proud though when you got it. Let everybody know that you got it. And then the outers, negative 3b. So you could write that as minus, or I wrote as plus a negative. That's either way is fine. The inners, 8b, and the lasts. And again, we could combine this stuff together. What two are like terms? The negative 3b and the 8b, when I combine those, what do I get? 5b. Everybody's okay? Feel good on foiling? Okay, so there are some shortcuts involved with foiling. You guys remember the perfect square multiplication patterns and difference of two squares multiplication patterns? Oftentimes we'll use them in reverse to factor rather than to expand. But they can be used in either direction. An equal side reads forwards to backwards or backwards to forwards, right? So if I wanted to do x minus 3 quantity squared, and I wanted to use the factoring pattern rather than rewriting it as a FOIL problem, oops, thanks for using that version. How would I write this?
X minus 3, x minus 3, x minus 3.
So in my formula, A is x and B is 3. So I'm just going to have x squared minus 2 times x times 3 plus 3 squared. Now you can do it what you're describing, Addie. That's fine. But look at how quick this was. Right? It's almost, you could do that in your head. You see the power of what we're describing? It's just a shortcut. Do you need to do it that way? No. Is it maybe convenient to be able to do it that way? Yeah. Okay. Let's look at the next one, y plus 5, y minus 5. Do you notice that this fits one of these special patterns? Yeah, the difference of squares. So if I didn't want to FOIL this, what would I write here?
Y squared. Oh, wait, no. Yeah.
So this is like my A and my B, right? So the formula says that this should be A squared minus B squared, right? So I should write y squared minus 5 squared? Or just y squared minus 25. Again, all we're doing is talking about a way to shortcut around foiling and just go straight to an answer. Ideally, these are things that you could do in your head once you feel practiced, right? Now, when you have a coefficient on your x, we have to be a little bit careful here. Which one is this? Which pattern are we looking at for 5? Good, perfect square with subtraction. So what is our A?
2.
And what's our B? and the b is 1. So if we go to our pattern, I'd have 2a squared minus 2 times 2a times 1 plus 1 squared. Everybody's okay with how I filled in? What's 2a squared? 4a squared. Remember, it's 2a times 2a. Bless you. It's a lot of them. And then 2 times 2a times 1 is 4a, and 1 squared, well, we know that, it's just 1. Does everybody feel okay? I think I'm going to skip the next one. Is that all right with everybody? We get this. It's review. Now we're going to go the reverse direction. We're going to worry about factoring. So the first one is x squared plus 4x plus 4. What does that factor to? It's a little
Plus 2 squared.
Okay, very good. So Daniel says x plus 2 quantity squared. That's correct. At this level, this type of factoring isn't, the expectation is that's a mastery skill, that you have mastery of that skill from Algebra 2. I know Mr. Boyle spent probably the better part of a month practicing this particular skill. The expectation is that you have it still, and you have it at a mastery level. That means you can do it quickly and accurately on request. Now we'll knock a little rust off here, but if that's not the case, you need to say something, and you need to come and get some extra help. The expectation is, after the amount of time you spent on this the previous course, that you have this skill and you can do it quickly and accurately. And it's not like, what, huh? That's not okay. Right? You spent too much time on that to walk away with nothing. Daniel, can you tell me a little bit about how you did that? What was your thought process, so that we can all kind of get caught up to the same spot if we're still a little rusty on this?
Yeah, so I kind of just did it in my head, like x is by itself, and I asked like what two numbers added to get 4, and then multiplied it.
Yeah, good guy. And which problem do we look to try to figure out first, the multiply or the add?
Add.
Well, how many sets of whole numbers add to give you 4?
Just multiply.
Yeah, you want to do multiply first, right? Because there's an infinite number of numbers that are going to, pair of whole numbers will add to give you 4.
Yep.
Right? 0, 4, 1 and 3, 2 and 2, 4, 0, but 5 and negative 1, 6 and negative 2. Like, it's unending, right? But the multiplication problem, there's just 4 options, right? 1 and 4, 2 and 2, negative 1 and negative 4, negative 2 and negative 2. So from that list, you would then check which one of them satisfies the addition piece. Gianna?
Can I do that?
Sure. And from there, it should be pretty easy to see that it's indeed 2's across the board, right? All right. 8 is a little harder. What makes 8 a little bit harder?
Number from Z,
Well, there's a number in front of the x on the previous one.
but it's a 2.
Oh, you mean the z squared?
No. Like 2 before Z does not affect it.
The 2 before z squared.
Yeah.
Yeah, because, I mean, there's a number before z,
Oh,
and that doesn't matter
that's
to
the
us,
square
right?
one.
Okay.
Is it because there's both addition and subtraction?
The addition and subtraction doesn't make much of a problem. The 2 in front of the z squared complicates the problem a little bit. Not so bad in this one, because what else do you notice if you look at all the coefficients? They're all divisible by 2, correct. What should we do as a start then if they're all divisible by 2?
Divide by 2.
Factor out 2, not divide by 2. If it was an equation where there's like a left side and right side, then you could divide and do things to both sides. No equation here. We have to factor the 2 out. So that's correct. That's called a greatest common factor. When I factor the 2 out, what's left?
Squared.
You mean z squared.
Plus 3C.
Okay. Everybody okay there? Okay. Now from here, we can do exactly as Dan suggested. We'll look for the 2 numbers that multiply to give us something and add to give us something. What do they have to multiply to give us?
Negative 54.
Negative 54. And what do they have to add to give us? 3. Notice with my z's, I'm going to put a bar through the middle so it doesn't look like a 2. I'm going to try real hard to not make them look like 2's. All right. Who sees it? Gabby.
9 names.
9 and negative 6 is correct. Now, you know why in elementary school they harped on you memorizing your multiplication table so hard, because skills like this are so much easier if you're stone cold on your multiplication table. If you don't feel good about your multiplication table, add you somewhere. Where is it? So fun. There it is. I have for you my touch and tell, where you can practice. So like 6 times 5, you push in and you can see the 30 through it. So who needs to practice their multiplication tables? There you go, Krista. All right. So we've identified the 9 and the negative 6. What is our final answer then?
2 plus 9 and
Z minus.
Keep in mind, we gotta keep that 2 that we pulled out front with us through the whole ride, right? Everybody good? Okay. What about 9? Can't factor out the 2. How does that change our process?
Don't you have to
Yeah, when you,
multiply the first one and the last one?
So now we're going to look for the 2 numbers that multiply the coefficient from the front times the coefficient at the end, but still add to give us the middle. Now, Mr. Kulik, why am I all of a sudden caring about why am I all of a sudden doing this? I didn't do it up here. But you really did. right? You really did. So it's not new. You just were sloppy about it before and didn't say that, which was fine because it was a 1, and multiplying by 1 does nothing, but you were doing it the whole time. Everybody okay? So just pointing out that nothing has changed, right? All right, what are the two numbers to multiply to give me negative 24 and add to give me 5? 8 and negative 3? Or negative 3 and 8? Does it matter the order I write them? It does not. What's the catch though? This, what's up?
In the equation.
So does this take me straight to my factored form like the previous one does? No. We have an additional step, right? What is that additional step? We have to write this as a factor by grouping problem. So what the 8, let's give me a different color actually. What the 8 to negative 3 do is tell us how to rewrite that 5. Is everybody okay there? Remember doing this? Oh, I hope it's been more than vaguely. Okay, what do we do now that we've rewritten it as a 4-term polynomial? If you combine like terms, you'll be right back to where we started.
Don't you do the parentheses?
So you make,
Oh, guys.
yeah, you make 2 groups. When you make your 2 groups, there must be a plus sign in the middle. Notice that I wrote this as plus negative 3b instead of minus 3b. See that? You did that on purpose because I know when I'm doing factor by grouping, I must have a plus sign there. So never am I going to write subtraction when I'm doing this. I'm always going to write plus a negative. It's okay? Now what do I do after I've made my 2 groups? I find the greatest common factor from each group. If I look at the first group, what's in common between 2b squared and 8b?
2b.
2b. Or not to be. Yeah, that's a literature joke for everybody. What's left after I factor the 2b out? b plus 4. Correct. And then the second group, what can I factor out? Negative 3. Notice it must be a negative 3. Just taking positive 3 will not work. What do you notice now?
B plus 4, B plus 4.
Yeah, the b plus 4s are the same. So those can act like a greatest common factor. When I factor out the b plus 4, what's left? 2b minus 3. Does that ring a bell? Okay. Who can do 10? Y squared minus 8 minus 20. Or sorry, y squared minus 8y minus 20. Somebody that hasn't been participating a bunch already. Charlie.
Is it y plus 2 and then y minus, or y plus 10 y minus 2?
You were right the first time when we started.
Y plus 2,
Y plus 2 and
y minus 10.
y minus 10. That is correct. Positive 2, negative 10, add to give us negative 8, or add to give us negative 8. And they still multiply to give us negative 20. Pretty happy? Not soon enough. It's an hour long today. Who can tell me how to do 11? You need me to do some intermediate steps first before you see it, that's fine. You can tell me how to start 11. Start it.
Do you divide by 3?
Nope,
No, you factor out 3.
not enough.
No.
Factor out an 8.
Factor out 3.
There, that's the Krista, that's got it. 3A, both of them were good ideas, they just weren't all the way there. Okay, who can take us all the way home now? Who can take us all the way home? Daniel.
Would it be 3a parenthesis a minus 8, and then parenthesis a plus 2?
Yes. So far, so good? If I look at number 12, 3 cosine squared x plus 13 cosine x plus 10. Like, what in the heck is a cosine doing in here? Well, the cosine is going to act like a variable, right? So on our first go around, let's just make this look a little bit more familiar. And let's replace our cosine x's, which is a different variable name. Let's call it a. So when I look at that problem, the cosines don't bother me. The cosine x, that's just a variable name. So I'm just going to think about it like I would like 3a squared plus 13a plus 10. Does that feel okay? Okay. So how would I go about factoring 3a squared plus 13a plus 10?
Multiply 3 or 10, and then time 1 plus 1 plus 13.
Yeah.
This isn't done.
Nope. That adds to give us 11.
No,
Not
not
13.
11.
Yeah, I used that.
Sure.
Negative 2 and 15.
Those multiply to give you negative 30,
Yeah.
not positive 30.
Oh wait, 32. 2
2 and 15 and to give you positive 17. That's needed.
Oh my gosh, 3 and 10.
3 and 10. That's the ticket. Okay. So we've done that. What do we do next? Make our two groups. What has to be in the middle of the two groups?
So,
Plus sign. Okay? From the first group, we can take out A and A. From the second group, we can take out A, 1. Notice that those two terms are relatively prime. That means they have nothing in common other than a 1. Still got to take something out, though. So how does this finish out?
A plus 1, 3 plus
Okay? A plus 1 times 3A plus 10. Close.
10. After cosine,
We have to put the cosine back in. So instead of A, we're going to have cosine x plus 1 times 3 cosine x plus 10. Does that feel okay with what we just did? Now, these special factoring patterns work, or the special multiplication patterns work backwards too as factoring tools. So if I look at x squared plus 10x plus 25, what I observe is that last number, the 25, is a perfect square. And the first number, x squared, is a perfect square. So my question to myself is, does 2 times A times B equal that middle value? Definitely does, right? So I have x plus 10 quantity squared.
did you get the 2 from?
You're asking about this 2 right here?
Yeah.
Right? I'm just checking to see if the middle works out with the A and B that I see. If it doesn't, what should I do? Back to the other type of factoring, right? This is a quick in my head check to see if I can get away with like, boom, going straight to the answer versus having to factor. Where this is really valuable is where you have a coefficient that's not 1. It can be a real time saver, right? If you have like 4x squared, minus something plus 64, and it's like, oh my God, there's so many factors of 4 times 64 is 256. It's like that's so many things I'd have to check to find the 2 things I multiplied to give me. It's like really frustrating. So situations like that, it really, if you can get away with just like one quick perfect squares check and it works, it's like, oh, what a lifesaver that is. How do we do 14?
Z minus 6, and then Z plus 6.
Perfect. So you observed that that was a difference of 2 squares. Everybody see that? Hopefully that's a factoring pattern that we all felt comfortable with, that Mr. Boyle drilled the rich side of you guys out. Yeah? Difference of 2 squares. How about 17?
You would.
I don't know.
Good. James says take a 3A out. And if you do that, the difference of 2 squares is now staring at you in the face, right? A squared minus 9. A minus 3A plus 3. Who can do 15 for us? It's got those scary cosines in it. Oh no! Should the cosines matter to us? No. Hopefully what you notice is that the first term is something squared, and the last term is something squared. So you just want to check to see if 2 times the first times the last, does that equal the middle? It does. So we can go straight to and be done. And again, that check that I wrote down is something ideally you're doing just up here, right? So you don't actually need to write that down. You can just do that arithmetic in your head, because, guys, 2 times cosine times 3. We can handle that in our head, right? Like, if not, ask them to touch it now, okay? All right, 18, who can do that one for us in your head? I hear people whispering the answer, like, say it loud and proud so everybody can be like, ooh, look at this, big brains on this person.
Cosine minus 6 squared.
Except,
Oh, sine.
yeah. So sine x minus 6 squared. Now I'll make a comment here. Students love to do this. What's wrong with what we just wrote? Where's the x, right? The x's need to be there. If you drop them, I'm going to make a deduction on a quiz or a test that's not correct without the variable. I'm telling you this right now to let you know that I will be picky about this, so that you, when you're practicing and doing your homeworks, you're able to know Mr. Kulik's going to be picky about this and keep an eye out for it. So that does need to be there. All right.
Wait, for the last one, didn't the 12 have to equal to a minus 12?
So, what do you mean?
In the actual problem, it's sin squared x minus 12 sin x plus 36.
Right. So what, I mean, like, you're looking at this part though,
On the whole.
because the minus was already in there, right? That's what you're, okay. So you're good?
Yeah.
Okay. I mean, you can think about them both as the plus one by just doing like plus a negative. All right. Now that we've reviewed basic algebra things, let's go on to combining those techniques with our identities here on our sheet. So have your sheet ready, because these are like the list of things that you can do other than, like FOIL and factor and the common denominators and that jazz. So if I look at this first expression, we have sine cubed x plus sine x times cosine squared x. The first thing I'm going to notice, or that I typically look for, is there an algebra thing that I can do? So if I see that I have 2 terms, right, I have something plus something else, usually the first thing I'm going to look for is, can I factor? is there a factoring that can be done with sine cubed x plus sine x times cosine x? Or cosine squared x?
No,
There is.
take out a sign.
There's a greatest common factor of sine x. That's correct, Gabby. Everybody see there's a sine x term involved with each of them? So I'm going to take the sine x out. What does sine cubed turn into after I factor a sine x out? Sine squared. And what does sine x times cosine squared x turn into? Say it loud, Julius. Cosine squared, right? Is everybody okay there? With what I've done algebraically?
Where's the sign?
What sign?
Yeah, I'm confused. How did you get cosine from sine times?
If I distribute this back through, I have sine times sine squared, that's sine cubed. I'd have sine times cosine squared, that's sine times cosine squared,
Oh,
right?
so you just take it out.
Is that okay? Now, what I'm going to do is I've done all the algebra things I can do, right? Because that's an addition sign, I can't do a difference of two squares. So now I'm going to go to my identity sheet and look for an identity. Because I have exponents, I have sine squared and cosine squared, I'm going to be looking at the Pythagorean identities, because those are the only ones that have exponents attached to them, and addition or subtraction. What do you notice if you look at the Pythagorean identities? I see that P1 says sine squared plus cosine squared is equal to 1. So what I can do is I can replace all of this with a 1. Ooh! That makes things simpler, right? Then what should I do after this?
Multiply
Yeah, what's sine x times 1? Sine x. Can we get any simpler than one thing? No. This would be our final answer. Yes, James? Absolutely. Does this feel okay so far? Let's look at the next example. Secant x minus 1 times secant x plus 1 all over sine squared x. Typically, the first thing I look for is algebra. Does anybody see a good algebra thing that I can do?
foiling the top two.
Yeah, foiling the top two seems like an excellent idea, because what type of multiplication is going on in the top two?
Foiling?
Well, it's a difference of two squares, right? I have secant x minus 1 and secant x plus 1. I love when I see a difference of two squares factoring pattern. That's almost always going to be something super useful for us. So that's where we'll start. Everybody okay with what we've done so far? You see I just applied the difference of 2 squared multiplication pattern to do that multiplication quickly without having to FOIL it out. Would it be wrong to FOIL it out? No, this is just quick. That's all I'm doing is trying to save myself a little bit of grief by using those patterns effectively. Okay? Does anybody see any more algebra you could do? The only reasonable algebraic thing I would see to do is that you could try to factor the difference of 2 squares back again, but now you're back to where you started. Probably not a great idea. Okay. Well, we've exhausted our algebra. It's onto the identity sheet. Notice in the numerator, I have squares and then addition and subtraction. When I see that, where do I look? The Pythagorean identities, the P's.
Because 10 squared plus 1. 2 is
Yeah, so P3 is the one you want because it involves a secant squared. What does P3 say secant squared is equal to?
10 squared plus 1.
So I'll replace the secant squared with tan squared plus 1, and everything else stays the same. Is everybody okay seeing the substitution that I made there? I'll try to highlight those substitutions when I make them so it's easy to see. And in fact, maybe we do this. This might even help. What if I write like the name of the identity that I used over the equal sign? So you can tell why this thing is highlighted, what happened. Does that help if you go back and look at this again? This is just me trying to make the notes more valuable for you. Do you need to do that when you're doing things? No. Is it maybe a good idea at the start, if you're like halfway through a problem and you're gonna have to come back to it? Might be, so you can figure out what you did. All right. What should we do next? I see a good algebra thing to do.
Subtracting.
Yeah, we can combine some like terms in the numerator, right? What's 1 minus 1? 0. Well, that's great. So now we have tan squared over sine squared. Everybody okay? All right, we're getting closer, right? This is simpler. The question is, can I get any simpler than this? So, another effective strategy when we get to this stage is to try rewriting things in terms of sine and cosine only. So if I have, there's no more addition and subtraction to do, there's no, things to combine, it's just I have, this fraction. 1 second, okay? And there are terms that aren't like. If I change the way I've written them, I can often write them as like terms so I can do something else. So if we look at our basic identity sheet, sine squared, I don't want to touch because that's already a sine. So I'm going to be looking at tangents, and I'm looking for one of these identities for tangent that relates it to sine and cosine, or cosine. So Kendall says, what if we use Q1 that says tangent is sine over cosine? That is the one that we would want to use. But Kendall, this is tangent squared. The sheet says tangent is sine over cosine.
Would it be sine squared over cosine squared?
It would, yes. That is correct. So as an aside, all of our identities in the reciprocal, the r's, and the q's can all work regardless of what the exponent is, right? Like tangent is sine over cosine, tan squared is sine squared over cosine squared, tan cubed is sine cubed over cosine cubed. You can just like add an exponent for any of the r and q identities, just like we've done here. Is everybody okay with what I've done? Or what we've done? We've done this as a group. What do you suppose I want to do next? What's that? Oh, okay. I thought you said something.
You get this sine squared.
Yeah. So that's exactly what I'd want to do next. So the way I think about this, is I'm going to think about this as two separate fractions. So I have sine squared over cosine squared on the top, and sine squared over 1 on the bottom. Everybody's okay with that? Since the sine squareds are both in the numerator of the respective fractions, I can reduce them out. When I reduce a fraction, what happens to the thing I cross out? What does it turn into? 1. So if I write this, I'm going to have 1 over cosine squared over 1. Because 1 over 1 is just 1. Everybody's okay with that?
You have to put this.
Well, I'm just showing my work here, right? Like I'm trying to really be intensely careful of showing my work. So when you go back and look at this, it's really super clear what I did. So like have to, no, right? Like no. But I'm going to do it this way because if you go back and look at this, it's not going to make a lick of sense if I'm not like including every little nitty-gritty. Does that make sense? So it's going to be longer than maybe it necessarily has to be, but I think that's what you want at the start, right? You'd rather have more detail than not enough, because you can't look at it well, you don't want to look at it, have to look at it and figure out what the heck happened. You want it to be super duper obvious. Does that make sense?
Yeah.
Okay. So this is really just that, right? 1 over cosine squared over 1 is just 1 over cosine squared. Now we're down to a single thing, right? A fraction. But what's better than a fraction? Not a fraction. So this has 1 over a trig function. When I see that, the place where I'm going to look on my identity sheet is the reciprocal identities at the top. Do we see 1 over cosine involved here?
Yeah.
Yes. I see R5 that says 1 over cosine is equal to secant. So 1 over cosine squared is going to be equal to secant squared. And can we do any better than one thing? Nope. We'd be done. I think I have 1 minute left in class. This feels like an excellent stopping point as we just finished this example. For next class, I don't want you to do anything.
No.
No. Not on this. Not yet. I want to spend a little bit more time building a little bit more intuition before I do this, because this is one of these topics that's really hard at the start and will get much easier as we go. I don't want you unsupported, doing the real hard at the start and getting super duper frustrated and giving up on it. So we're just gonna wait till next time, do a little bit more example, and then start in class where you have access to some support to make that initial step in, like toe dip into this topic a little bit more manageable. Everybody cool with that plan? Okay. You guys can